good morning, everyone. Hope you have had a nice first session during the morning. So let's go for the second session. So this presentation will be about mostly the PhD work of Tiago Santos, who is right next to me, where he's using source compilation for hardware and software co-design. But before he presents his work, I'm going to present the research group where we are working and tell a little bit about the story of why we are using source compilation and why we are investing on this. So first, who are we? So we are a research group, SPECS, which focus on systematically addressing non-functional requirements. So we have programs, we want to make them run more efficiently or faster or improve any metric, not only performance. We could also be trying to make code more safe, have less vulnerabilities. And in this research group, we have a close connection with people from the electronics department. So we also have research about hardware software solutions. So they we work a lot with custom hardware, custom instructions. So you can see that regarding architectures, we go from embedded systems, with RISC-V, FPGAs, and we also have work on high-performance computing. One of the things we do in this lab is that instead of working directly with the compilers, messing with these very complex, huge tools, we try to work on the edges. So that means working directly on the source code or working on the assembly, generated assembly, or any intermediate representation sometimes, but the rule usually is this. We try to be on the edges. Before I go to the source compilation, I can show you some, just to mention other work that we did that involves also GCC. So we had this PhD student working on flag selection and ordering. So the idea was, if we manually set the flags, can we get, for specific applications, better performance or better energy usage than using the normal O3, O2 flags? And the answer is, yeah, we could do this. Because usually these optimization flags, they have to work well for standard, for all applications, let's say. So it's more or less an average, but we can specialize them for specific applications. One thing we noticed, at least at the time, this is already a few years, this work, was that on GCC, we could not reorder the flags. So it seems that the pipeline was fixed. We could only turn off and turn on. And with LLVM, we could set the order of the flags. And this allowed to have more interesting results. Of course, the best results we had were like a 25% improvement, but over like O3. So I think it was an interesting result, and we could get better results when we were targeting less standard architectures or less known architectures. For instance, I think the best results we had was for PowerPC, which, okay, it's known and it's used, but it's not as used as x86. So probably the optimization efforts was focused more on those kind of platforms. So going now to the source part. So just to give an example, what do we mean by source? What we mean is that we have some source codes and we have a mechanism that allows us to change directly the source codes. For instance, inserting some prints in this case. So why are we going this route, right? So when we do research messing around directly with already existing compilers, or even in particular C++ compilers, we found several issues on our side. So, for instance, first of all, we lose some information. If we go to the internal representation, comments disappear, of course, after the preprocessor. And sometimes we wanted to have information about high-level structures, and we would lose that. So working with the source, we can keep all that information. One important thing for us, we are a research group that is not very big. We don't have a lot of PhD students, although we have several master students every year. And the masters that we receive, they have a lot of classes during 1.5 years, and then they have 5 months to do their work. So in 5 months, you can imagine that it's not a lot of time to learn a tool like GCC and then do something useful over it. So with this approach that we are using of modifying the source, we could really shorten that learning curve. In 1-2 weeks, they can already start doing some interesting stuff. Then we had other problem, which is, imagine that they do some very interesting work, some very nice package. How can we distribute this work to other people? How can other people use this work? And if we work directly with compilers, by modifying a compiler, usually this means, okay, you want to use our work, so please now use this specific version, modified version of GCC, and that is not very practical. By using transformations at the source level, this is just another tool in the tool chain. We can just have source at the beginning, apply the transformations, and then give it to the compiler. Also, we wanted to avoid being locked to a specific compiler version. Usually, if you modify a compiler, we have to be, all your work stays locked to a specific commit or to a specific version. And if we directly change the source code, that is not a problem. We are just locked to the version of the code standard. And also, if we implement some work on GCC, for instance, unfortunately, we cannot use Clang then, or Clang, or some other compiler. This is even even worse when you consider that in embedded systems, the toolchain environment is very fragmented. So this was really a problem for us. Okay, so there are other points. For instance, if we do some transformations, it can be easier for the user to at least have some information about what happened. We can do a diff on the code. Also, we have noticed it's easier to make integration with other APIs if we want to insert calls to APIs. But in any case, we see the source technology or approach as complementary rather than replacing, okay? So we have several works where we use this technology as a prototyping environment before going to the modifying things in the compiler directly. Just to present our family of compilers, we have two main source compilers. Cadabra is Java to Java, and Clava is C++ to C++. And we are using the same framework for building other compilers. So right now, we have also for Smalley, which is Android bytecode. So we can do also some experiments directly on APKs. We are starting a new one for Fortran called Metaphor, and we have another one for generic Antler grammars. So this common framework is called Lara, and basically the idea is we should be able to specify these transformations in a high-level scripting language, in this case JavaScript or TypeScript. This means that any work that a student or a researcher does can then be distributed using Node Package Manager. So this allows us to, if some student does a very nice work, 2-3 years ago. He can publish a package, and now you can reuse it as long as it's supported. And also, we try to outsource effort. So this framework allows you to use existing ASTs to do the analysis and the transformation. So you don't need to build the parser or even the AST. I'm going to present the source compiler for C and C++. It already supports a lot of code. I've been able to parse GCC with our tool. So we were able to run a script that inserted code that when we run GCC, it generates a call graph. So we have this in the paper. It has been in active development for several years, and we already have several packages on NPM developed by students, and he's going to present and use some of them. And we have integration with CMake, and I'll show you an example in a few minutes. So just to show you an example of what kind of script this tool accepts. So the idea is that we provide the tool the source code and the script will analyze or change the source code. So imagine that we want to implement the example I showed you before, where we have a print after every call, printing the function we are and the function being called. So the first thing is we want to do some search the AST. So we will import the query class. We want to target functions and calls. We want to find the functions and the calls inside the functions. So we are going to import also those nodes. And then first, we'll do a loop over all the functions in the codes. With this query.search, it will return all the functions that it finds in the source code. And inside this loop, now we can, from starting the search from each function, try to search all the calls inside the function. And finally, for each call, we can insert the printf with the name of the function and the name of the call. So this is a very simple example where we are directly inserting literal strings in the code, but we have other, for instance, an API for logging, where you don't have to directly put their printf. You just say, I want to log after this node, for instance. That abstracts these kind of details. I have here a very quick demo. So maybe make the letter bigger. So can you see this? Okay. So this is our web demo for this tool. On the left upper side, we have the source code that we want to analyze. On the upper right side, we have that code. And if we ask to, apply this script to this code, on the lower left side, we have the result. So we see the code, but now with the inserted code. And here we have the output. So very simple example. Going back to the presentation. Just wanted to show how can we integrate this kind of behavior, this flow with CMake. So because imagine, it's easy if I want to apply this transformation over a single file, but what if I have a very complex project, right, with a lot of flags and defines? If you are familiar with CMake, this is a very simple example. In CMake, we have the concept of a target. When we call add executable, we are creating an executable target, in this case, hello demo. If you want to apply a Clava script over this code, first you have to import the Clava package. And then we provide a function, clava_live, which you give it a target, and you give it a script. And internally, it will use all the information that CMake has about the compilation flow, call Clava over that code with those configurations, generate the C codes, and then redirect the generated codes to the compilation, to the rest of the compilation flow. So this way we can very easily integrate and apply this kind of scripts over C and C++ projects. So I'll finish just showing some recent works that use this technology. One of them, we had a postdoc working on auto-parallelization for C. So in this work, he's using Clava to analyze a for loop and determine if it can be parallelizable or not, and then automatically inserting an OpenMP pragma over it. So we have some experiments, we have some nice results on some benchmarks. Another work that we are doing is about making the same, trying to see if we can provide the same guarantees that Rust has, but on C. So the idea is to do the same kind of checks and have annotations that provide information that Rust also uses, like lifetimes. The state of the work right now is basically we have a borrow checker, but for C, that already can detect use after freeze and those kind of problems for individual pointers. We now want to extend this to support heap memory and arrays. And this is a very recent work, master's work that was defended this week on Tuesday. So using Clava scripts to analyze if a code is compliant with MISRC or not. We compared this with another checker that was implemented over a version of GCC, and we could have we could detect some cases that work was not detecting. Okay, so now I'm going to pass the word to my colleague.
Okay, so the things João was explaining before was basically the baseline of the compiler and some of our recent work. And I'm going to talk about my specific recent work, which is built on top of this compiler. And in particular, it's in the context of hardware and software co-design. So what exactly is hardware software co-design for those who are not from this specific area? So essentially, I have an application, C or C++ application, written for your typical CPU, and I want to accelerate it by offloading certain regions onto a hardware accelerator. So you can imagine that I run my application on the CPU, then I offload some computations onto the accelerator, that goes back to the CPU, and maybe I can even run some things on the CPU and some others on the accelerator. Some accelerators can be things like GPUs, DPUs, and so on, but we are specifically focusing on FPGAs because, as you might know, FPGAs can fit any kind of computation that you give it. So they are generic enough to accelerate just about any kind of computation that you may find in your typical C and C++ programs. The major problem with trying to automate this process is, first of all, trying to define what a region of code is for offloading, and then try to decide whether we should offload those regions or not, and then finally trying to optimize those regions for the target accelerator. And source-to-source can help us quite massively with this. So imagine that I have a dot product function, something very simple, and I want to accelerate this. What kinds of challenges will I find that can be solved by source-to-source? We can start with a simple one, which is to actually time this thing. So by using Clava, I can very easily say, please add me a timer over this function and report me the value when I run the program. I don't need to do it there by hand and write all of this. Another one is when I'm not just interested in this function, but also on the rest of the program. So maybe if I go beyond the dot product, but I will also find regions that are interesting for offloading. So if I map the program into some other representation, like a task graph, I can find that, okay, now I have some other tasks that initialize the arrays, then you have another task that calls printf, and so on. And for large programs, this can grow quite exponentially. Another thing, and this is specific to offloading code onto FPGAs, is that we need to generate a hardware design for that code. And the way that is done is through something called high-level synthesis, or HOS. I'm not going to bother you with the details, but essentially we need to insert a bunch of directives to try to expose some parallelism within the code. So basically giving the HOS tool some hints about, please apply unrolling over this loop, please map these arrays onto these kinds of structures, try to achieve this kind of pipeline, and so on. And this is a process that is traditionally done by hand, but it would be very useful to automate so that more people from the software side of things could use HOS in their flows without needing to actually understand exactly what's going on with these directives. And finally, we have the generation of all of the communication boilerplate between the CPU and FPGA, or another accelerator. So if like copying data to the accelerator, synchronization, running the kernel, getting back the results, all of that kind of stuff. This is an example from XRT, which is AMD's API for interacting with FPGAs, but it could be something else like OpenCL, it could be CUDA Intrinsics, or some other thing. Okay, I'm going to describe some code transformations that we have implemented for Clava, and which are very useful for this specific scenario, but also just as generic transformations that may be useful for multiple kinds of scenarios. So the first one is function outlining. What's function outlining? It's the opposite of function inlining. I try to find a region in the code that I want to offload onto its own function. This is something that you sometimes see when you use a text editor or an IDE where you have those extract method kind of things, but we are doing it over C and C++ and programmatically on a source compiler. So you define those directives, say, I want to begin here and here, please extract this onto a function. And it's going to extract it onto its own function and create a signature, the call, all of these kinds of things, including adjusting for any continues and breaks that may happen within the region itself. Another transformation is a little bit more radical, and it's called struct flattening, which is essentially getting rid of structs. Structs causes lots of issues when targeting an FPGA, because they may have fields that are pointers, and they themselves may be pointers, and we have indirect pointers, and FPGAs do not like indirect pointers. So one of the transformations we've done is to transform structs into variables. So on the right side, I no longer have structs. Instead, I have one variable per field of struct. And this is applied over whether it is a value, a reference, it modifies initializations, allocations, and so on. And also, of course, function signatures and function call. Another transformation is file amalgamation. So one very useful thing about Clava is that we are completely agnostic to the underlying translation units. So everything we apply applies over every file of the application, not just over one specific file at a time. This allows us to do things like combining parts of the application or even the entire application onto a single file. So if I have these three files with some interoperability through the external keyword, I can join them into a single file and solve all of these external keywords and set the right Clava variables. And also, of course, also pay some consideration towards static keywords that may have that may result in different implementations of the same function. But using the source compiler, we can always go around those things and come up with a version of the program that fits into a single file. And we have other transformations like array flattening, ensuring functions always return void, hoisting calls, and constant flooding propagation, which is more traditional. I'm going to try to show you a live demo of some of this, so that I don't just talk about slides. So if I come here, so João previously showed you the online demo, but this is the actual compiler running on your typical environment. this specific case VS Code. And what I'm doing here is something very similar to what João did. I am basically inserting a print every time a function is called. So I am iterating over every function and inserting the print. And I want to find a way to visualize what I'm actually doing on the compiler. So I'm going to add these things, which are akin to breakpoints in your typical compiler. I'm going to say, I'm going to stop the script at this point, see what it's doing, then I'm going to run the transformation and visualize it again. Okay, so it shows me here a link that's going to open an online visualizer that looks something like this. So on this side, I have the current AST active on the compiler, and on this side, I have the matching code. And I can hover over the AST and see what it matches in the code and vice versa. This is very useful for me to debug my transformations and try to understand what's actually happening. So if I click on continue, it ran the transformation, and as you can see, it inserted the printf over there, and also the matching node on the AST. Again, this is a simple example, but just as a way of showing how you can see what's going on and debug these kinds of transformations. As for the actual transformations like function outlining, they are very simple to use. So essentially, I'm just trying to find those two pragmas, where do I begin and where do I end, and I call the outliner. For an input source code, that can look something like this. I say, begin here and end here, and outline this into its own function. Okay, it ran, and somewhere down here, I'm going to see that it outlined the function, created a call, and put the function there. Okay, those were general purpose code transformations, but now we're going to tackle an issue that is more specific to offloading, which is how do we generate a task graph representation of an application. So why do we even need to generate a task graph? Because a task graph allows us to reason about the application using certain defaults that we otherwise wouldn't have if we're just working with pure source code. So imagine that you have an application like this, where I can kind of figure out some structure of tasks. So I say I have a function, then I set some filters, and I have another function call, some filters, so on and so forth. The computations here are very well detached from each other. It's a very well-behaved source code. And mapping it onto a task graph is as simple as this. What's the problem? When you try to create a task graph for any C or C++ application out there, they don't usually follow this kind of structure. They weren't written with a task structure in mind. And so our challenge is to try to come up with a method for generating a task graph for any application. And our solution for this is to try to bring the C C++ down to a subset that exposes task structure for us. So by using those transformations that I mentioned, and in particular the function outlining, we come up with sort of subset where we either only have functions that only have computations, so functions that don't call other functions, the with functions of a call graph, for instance, or we only have functions that call other functions. So these functions by themselves don't really have any computations. They may have some basic control flow, shallow, only one level, and they only call other functions. And by keeping our application within this format, we can generate a task graph for any kind of application. So how do we actually generate a task graph? So we call this an extended task graph because we are doing things that typical task graphs don't tend to do. So if you have a function f1, we start by creating a matching task called F1. And inside of that task, we are going to have task F2. So because F2 is a call within F1, F2 will be a task within task F1. So the task graph is hierarchical. There are tasks that have other tasks inside of them, and so on and so forth. Tasks F3 and F4 are independent of each other. So you can just consider them as being two separate tasks, each of them with 100 iterations. Tasks F5 and F6 do have a dependency, so F5 must execute before F6. And so we outline this into their own task, and we say that within that task, we're going to have tasks F5 and F6. And finally, we have task F7. And we mentioned here that the extended task graph is an overlay of the AST. And why is that? Because everything you do on the graph space is reflected on the AST space. So if you take two tasks and you merge them together, you are basically doing function inlining on the AST. And if you take a task and you split it into two tasks, you are doing function outlining. And this allows us to basically change the granularity of the task graph whenever we want. So if I have a very sequential sequence of tasks, like I have over there, T1, T2, and T3, and I want to try to find some parallelism, I can maybe increase the granularity of T2. I go to T2, I split the task into 3, which on the AST is the equivalent of outlining. And potentially, I may end up with tasks that actually have some parallelism. That would be very useful in the context of trying to offload some onto an accelerator and keeping others on the CPU. Finally, we also show some that you can annotate these extended task graphs. And one kind of annotation that we find very interesting is annotating a task graph using the results of profiling. So if I run the application using something like perf or gpref, I get a call graph with the percentage of time spent on each function call. And by matching it onto the task graph, I can annotate the task graph with the percentage that the task would take on the CPU. And this can be very useful when trying to figure out which regions should be offloaded, because this will point me towards a hotspot on the program. Let's quickly look at the demo of how we generate the task graph. So again, when you use our packages, usually we need to use some very simple scripts to actually call the contents of the package of your source code. In here, I am first running the transformation flow to bring the source code down to that subset I mentioned, and then I'm generating the task graph. So here are some of the transformations done on that subset. So reflattening, constant folding propagation, sort decomposition, and then some constant folding propagation again. And my input source code is that previous source code I mentioned. Yeah. So basically this, and we're going to see what's going to happen when I generate the task graph. So it's converting the application down into the subset, applying the transformations. And then it puts the task graph. And the outputs are quite thorough. So because this is an AST, we can output the equivalent source code at basically any time we want. So every time we modify the AST with a transformation, we output that code as a way of also debugging the code and see what's happening. So you can see the output it created. First, it runs the normalization, then each of the transformations, and then some function outlining. So for instance, at this stage, what it did was to come here and say, I'm going to take these filter initializations, and I'm going to annotate them with this directive saying that I want to offload this. And then on a subsequent step, they are already outlined into their own functions. And the task graph itself is also generated here using multiple levels of zoom. And I can come here and see exactly what's being communicated, keeping track of names because some data may have one name on one function, but when you use it to call on a function call, it may change its name. Keeping track of names on a source context is quite important. And knowing these edges allows us also to trace the lifetime of data throughout the task graph. Okay, now I'm going to talk a little bit about how we can also integrate Clava with other tools. So one of the integrations we have is integration with VitisHOS. So VitisHOS is AMD's high-level synthesis tool for FPGAs, and we use it a lot in this kind of process because it allows us to get estimates of the performance that the code region will have on the subsequent hardware circuit. So we can run a transformation that does insert some directives for Vitis. It outputs the C and C++ code. It goes through Vitis. Vitis creates the circuit and reports back with the estimated performance. And based on that, we may decide, OK, this is good enough. I'm going to accept it. Or no, this isn't good enough. I'm going to change the parameters a little bit and tell Vitis to synthesize it again and keep going back and forth. So essentially, it's a design space exploration flow where I can iteratively interact with vendor tools in order to try to find a solution that I am happy with. And this is possible because you can essentially output just certain portions of the SD. You don't need to output everything. You can just output the little bit of code that you want and then pass it on to the other tools and integrate it back. Another integration we have is with another social source tool called ScaleHOS. It's also used in the context of FPGAs and high-level synthesis, but what this tool does, something a little bit more specific than our source compiler, because it starts by converting the code onto polyguys, which converts it into MLIR. And then from MLIR, it outputs, once again, C and C++ that has been optimized for FPGAs. And we use it as part of our flow because we can, if we find a function that we want to optimize, we send it to ScaleHOS, and then we can parse the result of ScaleHOS and integrate it into our AST without needing to restart the compiler or do anything, any sort of integration. Okay, I have talked about code transformations, generating task graphs, and integrating with vendor tools. So let's try to combine all of this into an actual hardware and software Codesign flow. So from a C and C++ application, it can be anything that was written for a CPU, which is most of them. I'm first going to apply a series of code transformations to bring it down to my subset. So I'm going to amalgamate the code, apply struct flattening, function outlining, reflattening, and so on. This also has the advantage of reducing the entropy of the AST, which makes it easier to write transformations because you have certain assurances, certain defaults that you otherwise wouldn't have if you were considering every kind of way there is to initialize a struct or every single way there is to initialize an array or indexing or whatever. Then I'm going to generate a task graph using that method I mentioned. And then I'm going to have some kind of algorithm or policy that's going to look at the task graph and try to find the regions for offloading. So in this case, you can imagine that the green regions were the regions that the algorithm found that would benefit the most from acceleration, and the red regions are the ones that remain on the FPGA. But once the algorithm or policy, it doesn't need to be something that complicated, finds the regions, it's going to make them ready to go through the vendor tools for eventually generating the hardware design. And that's where the rest of it comes in. So we also generate the backend, so all of the communication between the CPU and the FPGA, which can be stuff like I mentioned, XRT, OpenCL, or some other API, and you're going to end up with two separate artifacts in the end. The code that remains on the CPU, and which can be compiled using your typical GCC, and then the code that goes to the accelerator that needs to go through the vendor tool. And finally, let's try to see this in action. So I am using the same application as before, so our edge detection application. And I am saying, okay, I want to find regions for offloading this application, and I want to use the XRT backend. My algorithm or policy is to offload these two tasks. So I'm not letting the compiler decide. I am deciding. I want to offload these two tasks. And I want to target this specific embedded hardware platform. I'm going to run it. Once again, it's converting the application down to the subset, generating the task graph, and then doing the actual offloading. And if I come here to my output, I'm going to say that I have a new folder called clusters. That's going to tell me exactly what was offloaded. So I told it to offload the edge detect and the convolution, and it created me a cluster of tasks with exactly those two tasks. So it didn't find any issue with the dependencies or any other restriction. And in terms of the source code, I have a new version here with those different artifacts that I mentioned. So I have the code that goes onto the accelerator, which is essentially those two functions, the convolution and the other function, which are wrapped by this interface function. I have all of the communication boilerplate isolated into its own file. So all of this communication stuff that was generated programmatically by the compiler. And then finally, the whole source code that remains on the CPU. And one thing we did was to programmatically, through a compilation flag, define whether we want to run the original application. So basically, say, if I don't pass it the offload flag, I say, okay, just run, pretend nothing happened, and just run the original. But if I define the offload flag, it's going to call this one, which is going to call the communication, and then expect that the FPGA component is also up and running. Finally, I'm going to show you how we can use annotations in this process. So I'm adding a decorator to the task graph that's going to annotate the task graph with information from Vitis. So it's going to take every task, it's going to synthesize every task, and it's going to annotate each task with its predicted latency. So latency is the time it's going to take to execute on the FPGA. And once again, I say I want XRT as my backend, and I want to select the task with the highest latency, and only that. Then and then the platform again. Once again, brings it down to the subset. Showing the task graph and then the cluster. So typically this process would take around 2 minutes because synthesizing code takes a little while, even if it's relatively small functions. I had the results pre-cached, so we won't waste that much time here, but typically this will take a couple of minutes. And on my results over here, I can see, first of all, that it found that to the convolution is the task with the highest latency, and so it offloaded that. And also, I can see the result of the decoration. So, for instance, if I come down here, not here, decorated, you can see that my task graph was annotated with the latency estimate for each task. So it says this task is expected to run in 0.7 microseconds, so on, and it found that the one that takes 47 milliseconds is the one that should be offloaded. And also have some estimates about the resources that task will take on the accelerator. Okay, we are pretty much done. Just some quick acknowledgements to my PhD advisors, João Cardoso and João Bispo. Also the guys that give us money to do this, and of course everyone at Specs Lab. We have been working on Clava for the last almost a decade, and without them this wouldn't be at all possible. Okay, thank you for listening, and if you want to check out Clava, there's a QR code over there, and from that you can find pretty much everything else because it's all neatly centralized in our README. Okay, thank you.
Do you have to do something special for indirect calls or dispatching calls in C++, for example?
Okay, yeah, you caught us. That's something that we're considering. So everything we do here targets a certain subset of the language, right? There will always be features that we're not supporting because this is an academic project and we don't have the wherewithal to try to support everything. And that's one of the things we are not really considering at this moment.
Thank you.